Next up is Charles' Law for our gas laws. This is the one that you remember from the playground when you were a kid. So when you took that basketball out in the winter and tried to dribble it and it didn't bounce back up to you, that's because volume changes with temperature. But volume and temperature, unlike unlike Boyle's law, where volume and pressure were inversely proportional, volume and temperature are directly proportional. So if one gets bigger, the other one also gets bigger, right? And vice versa. If one gets smaller, the other one gets smaller. So you're going to have problems that look like this. It says a balloon filled with oxygen gas occupies a volume of 5.5 liters at 25 degrees Celsius. What volume will the gas occupy at 100 degrees Celsius? So you set up the problem just like before. You collect what you know. Volume 1 is going to be 5.5 liters. Temperature 1 equals, it says 25 degrees Celsius. But the other thing you need to know about this is, unlike volume, where you could use whatever unit you want, temperature, you have to use Kelvin. So although it says 25 degrees Celsius, I can't use 25 degrees Celsius and make this work. Now the reason I have to use Kelvin and I can't use Celsius is because Celsius has negative numbers. If I ended up with a negative number, that could end up in my equation giving me an answer for a negative volume, and that's not even possible. So I have to use Kelvin so that there are no negatives. So I'm going to have to add that 273 to my 25, and that's going to give me a 298 Kelvin. And then new volume I don't know, that's what I'm trying to find out. New temperature I do know, but that's going to be 373 Kelvin. Right? Still got to add the 273 to it. So setting this up, volume is 5.5 liters over 298 Kelvin equals my new volume, x, over 373 Kelvin. So I just got to multiply, divide, and get an answer. So hold on a second, I got to grab my calculator, forgot it. Across the room. But if I calculate this real quick, 5.5 times 373, divide that by 298, I'm going to get 6.88422. Again, I'm really only going to need 2 sig figs because of my 5.5. So 6.88 really turns into 6.9 liters. And that's going to be my answer. So just be careful on these ones because you have to change temperature to Kelvin. Otherwise, it looks like the temperature got 4 times bigger. So you would think maybe the volume should get 4 times bigger, but it doesn't actually work in this case, right? Because 373 is not 4 times bigger than 298. You can only do that kind of work if the temperatures in Kelvin to begin with. If it was 25 Kelvin to 100 Kelvin, that'd be fine. But gotta change your Celsius to Kelvin first, every time. So one more example. A sample of nitrogen gas is contained in a piston with a freely moving cylinder. At 0 degrees Celsius, the volume is 375 milliliters. To what temperature must the gas be heated to occupy a volume of 0.5 liters? So again, just collect what I know. I know an initial volume is 375 milliliters. My final volume is in liters here, so I need to write it in milliliters or flip the other one. It really wouldn't matter which one you did, but I'm going to change it to milliliters. I'm going to call it 500 milliliters. I do have to remember that I had 2 sig figs, so I might need to mark over this 0. Otherwise, the original temperature was 0, which is 273 Kelvin. And the 0 went to the 10th place, right? I had to add that 0 to make sure you knew it had significance. This still only goes to the ones place, so I actually can keep all 3 sig figs for this number. Otherwise, I did mark that incorrectly. It's not T2, it's T1. T2 is something I don't know. I gotta find that, right? So that's gonna be my X. Otherwise, just plug in values that you know. 375 divided by my initial temperature, 273, equals 500. Again, remember it's got 2 sig figs, divided by X. So I can solve for an answer here. 500 times 273 divided by 375 gives me 364. So 364 Kelvin. And technically I need to round it to 2 sig figs, so it's only going to be 360 Kelvin. If I wanted to, I could subtract 273 from that, so I would know that it's around 90 degrees Celsius. Because again, if I was subtracting, I'm stuck in the tens place now that this 6 is in the tens place. But if I wanted to know that that was about 90 degrees Celsius, I can do that, right? But in this case, it just said what temperature, so I can just leave it in Kelvin. You could keep this answer and be done. All right, so those are some examples for Charles' law.